watching the game. The Falcons were up by 8 and had the ball in their possession, and there was like a minute and a half left in the game, and I was like, they got this. So I just like went to the grocery store to look in,
Nope.
and I come back and they lost, and I'm like, what the fuck happened in that minute and a half? What the fuck?
Nope.
Just run the clock down. Jesus Christ.
Okay, so you guys had homework number 1 due this past weekend, and homework 2 is up already. Homework 1 solutions are up, homework 2 is up. I'll be finishing with the conceptual portion of homework 2 today, with talking about charging by induction. You also need to know about that for your lab this Wednesday. In fact, it's a 2-part lab. If you're prepping in advance, make sure you don't forget the second part, electrostatics and charging by induction. So we'll get that information out to you today. And then we'll move from the highly conceptual track that we've been on the last couple lectures to the highly mathematical by integrating continuous charge distributions. So you will find that as a significant portion of your homework number 2, perhaps even more of the percentage of the problems than you might expect, simply because it's very difficult to ask you about conceptual questions on web assignment. Doesn't mean it's not important. For instance, on exams, where I can ask you to write essays and things like that, you will see the conceptual stuff of homework 2 as well. Okay, so any questions before we get started? All right, so here's what we have. We have an object A. All it has to do is be charged. Did I say that's positive or negative last time? I want to do the same thing. Negative. Okay, so let's do it negative. So this is an object that has an excess of electrons. It has more electrons than protons. It doesn't matter what it is. It can be an insulator. It can be a conductor. Its only job is to sit there and be a charge. Then what we're going to do is take object B and charge it by induction. It is currently neutral, and as you will see through the process, it also is required to be a conductor, otherwise this won't work. So let's go through the steps of charging B by induction. So first, you bring A nearby to it. What that has the effect of doing, as we talked about, is charge polarizing B. So this will be plus, 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 minus, 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 something like that. So we bring A nearby, it charge polarizes B. Now, B is still at this point neutral, but all the pluses and minuses are not intermingled on the microscopic level. We do now have that there's more plus on one side and more minus on the other. We've created ability to maybe create a net charge. Again, it's still neutral, but we have separated a positive and negatives distinctly across the two sides of the object. So now what we do, we connect B to ground. So you may have heard this called electrical ground. It literally means connecting something to the ground, like put it in the dirt, okay? The way we symbolize that is like this. That's the electrical symbol. Really all we're doing is we're connecting B to a large neutral object, okay? So we're connecting it to a large neutral object like the Earth. You actually won't use the earth in your lab on Wednesday. You will actually use a kind of a metal cage, which is not even that big, but it turns out to be big enough for the purposes of the experiment. The purpose that it serves is that it can be a source or sink for electrons that still stays neutral. That is the purpose of a ground connection. If you want to send electrons to it, then you can send electrons to it, but the object is so big that essentially they dissipate, go away, and you haven't charged the earth. The earth stays neutral even though you've put electrons onto it. Or vice versa, it's somewhere where you can get electrons and yet remains neutral. It's just a big object where whatever charges you want to send to it or get from it, it doesn't appreciably affect the earth itself, okay? So in this case, what's the connection for the ground for? Well, these electrons that we've pushed to the right side of the object, the right side of the charge polarization, of course they repel to the far right because that's as far as they could get away from this negative, right? So this negative repels these negatives, and before the ground connection was there, this is the furthest they could get away. Well, now they can get away further. So those electrons will not just be repelled to the far right side of the object, they'll be repelled right off the object into the earth, and bye, see you later, they're gone. Okay? So we've gotten rid of them. So by connecting B to ground, what that does is neutralizes half the charge polarization. So we have now created a net charge on B. B is no longer neutral but charge polarized. B actually has a net positive charge. Okay? So we have succeeded in our task of charging B. We just have to make sure to now clean up after ourselves in such a way that it doesn't undo the whole point of this, which is to leave a net charge on B. So the cleaning up after ourselves, so now it's B is charged. By the way, it's worth noting that it is positively charged, and the general pattern here is that B will always wind up with the opposite charge of the object that you brought nearby. So it's charged opposite that of A. So essentially, where are you getting the charge that remains on B? It's the charge that was attracted to the nearby object. Okay? So you might ask, well, why don't these positives repel each other? Well, they do. That's why they're not all sitting right on top of each other, but they're more attracted to this negative, so they don't take the opportunity to flee into the ground. Whereas the negatives, the like charge, so the charge that is the same as this, that half of the charge polarization uses the opportunity to get away. Okay? So make sure you understand that if you bring an object A nearby and you do this process, the charge on B will wind up always being opposite signed to that of A. You can work through all this logic in reverse. Convince yourself that if you bring A nearby and it's positive, B will wind up with a negative charge. In that case, instead of electrons being pushed into the ground, electrons come up from the ground. Okay? So let's now clean up after ourselves. First, we're going to disconnect the ground. So we prevent further escape. So we can disconnect the ground wire. And then finally, we remove A. A doesn't need to be nearby anymore. A was kind of like the bait, so now we get rid of the bait. So what do we have left? We have positive charge on B. Now that there's no reason for it to hang out on the left side because we've taken away A, the charge will redistribute onto the outside. So this will be what B ends up looking like. So whatever excess charge has developed on B will now, of course, spread out. Notice that if the ground connection was still there, there'd be no reason for that charge to not just dispel across the entire surface, but it would go right into the ground, right? Or if we're talking about the mobility of electrons, electrons would actually come up from the ground and cancel all that stuff. So it's really important that you don't accidentally reverse step 3 and 4. You gotta first disconnect the escape hatch so that you trap the charge on there, and then you remove the bait so that the charge can redistribute. Okay? Does that make sense? That's how charging by induction works. Okay? And you can probably already see, but let me iterate why this has to be a conductor. Essentially, you are connecting one spot on this object to the ground, and depending on the fact that charge has the mobility to get from whatever part of the object to whatever other part of the object so it can escape, right? We had that all of these had to be able to get over here. So there needs to be mobility, okay? So there's only a single connection that this object has to the ground, and you need to have the mobility once you're on the object for the charges to travel from one part to any other part so they can actually take advantage of that escape hatch. Okay, so it has to be a conductor because there is only a single point that is the actual ground connection. Even if you were going to connect it to a bunch of points on the outside, the interior, of course, still would not be connected. So basically, you need to have charge mobility in the interior. Are there any questions on that process? Yeah.
Does it matter where that point is on the object when it hits the ground?
It actually does not. So even if you connected it seemingly weirdly over here, right? Now I connected over here, so it's kind of easy to imagine the electrons shooting over here. Even if you connected it right in the front, everything would just shift to take advantage of that, right? So if you have full mobility of those charge areas, they can all shift as needed to take advantage of a ground connection anywhere. Question?
Isn't it gonna make it like the amount of charge that the positive charge is gonna have? Is it gonna be like half of its charge, normal charge, right? Because it was neutral at the beginning, but it became half of the strength at the beginning.
Well, remember that this plus and this minus, that's not the entire charge that's on the object. This is however much charge is necessary to shield the interior, right?
Okay. Yeah.
Remember we talked about charge polarization. It's not all the charge, it's just enough to make sure that no other charges in the interior want to participate. So that's actually one of the questions on the homework. How do you generate more charge on something? Well, you can play around with how close you bring A. Okay, I don't want to give the whole thing away, but you can follow the logic of if you bring A closer, how much charge polarization you get, and if you take A further away, how much charge polarization you get. The amount of charge that will polarize will depend highly on the proximity of A. And then once the charge is polarized, of course, half the charge polarization becomes, half of it's neutralized, the other half becomes the net charge on your object. Yeah?
So if A is positive, then the positive charge on B will escape, and then the negative.
Right, exactly. So if this was, A was positive, it would polarize like this, and you'd end up keeping around this charge. That would end up being your charge polarization. This charge would be neutralized, not because positive charge has any mobility, but in this case, electrons would come up from the ground to neutralize them. So remember, it's electrons that are actually doing the moving and the shaking. So electrons are either being sent into the ground or being summoned up from the ground to cancel off the charge on the backside. Any other questions? Yeah?
If you connect it
Oh, you mean like if you connect it here?
Yeah.
So, ironically, what would happen is that the electrons that are in the front here, they would, so you might think, how does this electron get all the way from here to here, right?
Yeah.
Well, there is an electron that's right here that is happy to go, but then that means that the next one will shift in line, and so basically, you would end up everybody having just shifting over a little bit, and that would be equivalent to what just did. So you have to remember that the whole thing is filled with electrons, and so no matter where you connect the ground, there's always electrons that are ready to flow off right there. Okay, so it's not just over here. Yes, you have an excess of electrons, but there are electrons everywhere in here. Right? This interior, which looks empty, it's not really empty. It's minus, plus, minus, plus. I mean, there's still matter there, right? So there's electrons available anywhere. So they can always get off from wherever you connect the ground. Okay, yeah.
We're going to neutralize half the charge polarity after we disconnect and remove A, then we end up with some charge polarity again, but it's half, or no.
You're saying, is it?
Like, I know you have it's all plus on that B after step 4.
Right.
They're
That's just this charge was redistributed, right?
right, and some of the shielded electrons would now kind of go, or maybe, oh, it wouldn't unless there's something around, if there's a field. Okay.
Yeah, I mean, I'm assuming that I'm taking away A completely away.
Yeah. Okay.
So there's no reason for this to not just repel itself and go onto the surface to maximally get away from each other.
And so I'm kind of process half the charge polarity. So whatever our charge polarity is, it's half. But we're not measuring charge polarity yet, or are we?
You mean how much does it polarize?
Yeah.
We're not ever going to get quantitative with it,
Okay.
except for there's one exception which we'll do later around homework 4. It's just how much charge polarization you get will depend on the proximity of A.
Okay.
And I don't want to give, it's just an increase or decrease. It's never like compute the amount. So we don't have the tools yet to do that. I don't want to give away that homework question because this is one of the few questions that I can give you to extrapolate a little bit forward from this instead of just totally, regurgitating the process. Okay, so let's make sure we have enough time here to start with our continuous charge distribution stuff. That is a large part of your homework number 2. So continuous charge distributions. So this is where instead of having 1-point charge or 7-point charges, what we call discrete collections of point charges, where we can count them, this kind of stuff you're doing on homework 1, where you're trying to figure out what is the net electric field due to these collection of point charges. Now we're going to start smearing our charge around like butter on toast so that it occupies a continuous shape. So what do we do there? All we have to do is we have to take our fancy electric field formula for a single point charge, and then we basically say if we have some kind of crazy charge distribution where it's all kind of smeared out like this, well, we can of course think of some continuous charge distribution as just a sufficiently large collection of point charges. So we can kind of basically think of it as just a sufficiently large collection of point charges. I'm going to call each of those charges dq. So this will be dq. And each of them will have a small contribution to the electric field dE. So if we go over here, for instance, and we're interested in the electric field at that point, we think of the object as a collection of point charges. Let's say this one that I just labeled. That's going to make a small contribution dE like that. It's a positive charge. It's radially away. I would, of course, have to measure the distance r I am away from that contribution. And then I just basically integrate all those contributions. So basically, I integrate all of the dE's to get my overall electric field. So this is mainly going to be a mathematical exercise. This is not that much physics. It's really just using the point charge formula. It's just a bunch of math. It'll make your calculus instructor proud. This is why you have to have had calculus too, because we do some pretty involved integration. So here's how it's going to work. I'm going to do some for you. I'm going to do some of the most important charge distributions for you. You get a sense of how the technique works. But when I get the results, you don't have to reinvent the wheel on the homework. I actually give you the equations for some charge distributions on the equation sheet. So if you see those on the homework, just use the formula. You don't have to reintegrate. So basically on homework 2, you'll find more or less in the first half, you'll find stuff where I've already done the integration for you. You don't need to replicate it. Just use the formula. And then in the second half, it's charge distributions that I didn't give you the answer for. So you're going to have to set these up from scratch yourself. So these, the things I'm about to do sort of work as derivations of formulas that you're allowed to use. But they also work as showing you how the process goes, so that if you need to integrate your own, then you know how to do that. I'm going to do them in what I think is the most logical order, not necessarily the easiest ones first. So I think the first one is going to be one of the more awkward ones, but it makes sense for other reasons to do this one first. What I want to do is a line charge. So I'm going to smear my charge along a line. And the line charge is going to be, it's going to look like this. Let's make it positively charged. And that line charge is going to have a length of 2d total. Now that might seem awkward, that it has a length not of d, but of 2d. But the reason why is I'm about to split it in half, and then my integration bounds can go from d to minus d. Okay. So it has a length of 2d. I'm going to be interested in the electric field on the perpendicular bisector. Okay. So what is the electric field on the perpendicular bisector? Which is to say, I'm moving along a line that is perpendicular to the line charge, and that exactly splits it in half. In fact, I might as well go ahead and add my axes to it at this point. I'm going to set my x-axis like this, my y-axis like this. Now I have to tell you a little bit about how we quantify charge when it's like this. We have a couple different ways to do that. Of course, I could talk about the total charge. This thing has a total charge Q. I can think of it as having a length 2d, but I can also divide the two and get a measure of the charge per length. Okay? So we give this a name. We call it lambda. So lambda is the linear charge density. It's how many coulombs are carried per meter. That's useful for things that are where the charge is smeared out along a single axis. Okay? So generally speaking, for this, I'm going to assume that it has a uniform lambda. So I'm going to assume that when I buttered my toast here, I'm going to assume that I have a nice even distribution of butter. Okay, it's not lumpy. All right. And I tried to draw it that way as well. I didn't have the pluses along that bar kind of lumped into particular spots. Okay. this is generally speaking is the length of the whole thing. I should briefly address what if it's uniform, then there's no difference between taking the entire charge over the entire length, or I can take any little bit of it and any little length of it, and of course I'll get the same measurement. Okay? So if you're looking at the density of butter on toast, you can look at the whole piece, or you can look at any spot, and if you've buttered it nice and evenly, it shouldn't matter. So right here, if I take a little bit of dq and a little bit of length, dl, I should get the same measurement for the charge density. So there's no difference there. If it's non-uniform, which is to say that I've somehow made the charge distribution lumpy, you can certainly still take the total charge over the total length, but that will only give you the average charge density, which is not all that useful. So you can still talk about the local density. So at a particular spot, you can take how much charge is at that spot divided by the length of that spot, and you can get the local density. This will be the local density. It is actually a function of where you are on the object. You can then take the formula and invert it, and you can get the total charge like this. You have to integrate the function. Remember, this is a function now of where you are. And if you integrate lambda dl, you will get back the entire charge. So if you're looking to find the total charge, you can do that. Of course, that works over here as well. The only difference being that if it's a uniform lambda and it's the same throughout, then of course you just get back this, which is the original statement right here. So it's nice to see, of course, the uniform case is just a special case of the more general non-uniform case, right? So you'll have both of these coming up. I don't want to, I want to mention it at this point just because it's a good juncture to mention it, even though in my case I'm going to assume I have uniform charge density. So if I wanted to get the total charge, I would just multiply how many coulombs are carried per meter times the length of the whole thing. It'll get me how many coulombs are on that thing. So we'll do a non-uniform example. I won't do one of those today. So let's get back to the situation at hand. So essentially, what I'm doing is I'm going to pick a DQ, and this is going to be as arbitrary of a DQ as I can. I don't want to accidentally pick a special case. And I'm going to ignore the whole rest of the bar. I'm just going to look at this as if it's a point charge. And that is going to make a contribution to my electric field here. So I go ahead and sketch this in. This is how far away that charge is from the point of interest. And then, of course, since it's a positive charge, it makes a contribution which is directly radially away from it. So that's your dE. And our whole goal here is to figure out how to express dE in such a way that then we can integrate across all the contributions from all the charges along the bar. So let's do it. First of all, this is diagonal, so I don't like that. I'm going to break it into components. here's my DEX and DEY. So, my electric field has an X component and a Y component. And of course, if I pick an angle theta here, let's say this is theta, then this will be, let's make sure to get this right, this is a dE cosine theta in the positive I hat, and then looks like a negative Y component, so minus dE sine of theta j hat. And of course, I can factor out the common dE, and that's what I get. Incidentally, this vector in parentheses, what is its magnitude? 1. This is actually, for those of you that may be comfortable with this is r hat.
Mm-hmm.
This is a unit vector that places the size of the contribution in the correct direction. So that's this thing right here. Just make sure that our contribution points the right way. Now, if you aren't comfortable with that, then it doesn't really matter that you call that r hat or not. You just, of course, make sure that you get this vector points diagonally. Part of it's in the x direction, part of it's in the y direction. And the cosines and sines help you do that. All right, so now let's put in the formula. Of course, we have kq over r squared, and this is going to be dq, like that. So that small contribution to the electric field is made by that small bit of charge, dq. All right? So we can integrate at this point, but we've got this total mishmash of variables. We don't have a theta d theta. We don't have a q dq, right? It's all like some weird mix. So we need to kind of put it on the same page. And I think that's the hardest thing about this stuff, is to figure out how to get everything to be talking nice to each other. So let's start with dq. So that's the amount of charge. So I want, instead of to talk about the small bit of charge on that spot, I'm going to talk about the small bit of length. So that's dl. In my case, I don't really need to call it dl. I already named that axis. Where does the charge actually lie? This is a small bit of which one? dy, right? So in my case, this is dy. So this is how I turn this situation into a length integration. And you can probably see what I'm going to do. I'm going to integrate along the y-axis so long as I have charge on it, right? What are my integration bounds going to be for y?
Negative y to positive.
Negative.
Infinity to positive infinity.
Well, the charge doesn't go all the way to minus infinity. It goes to what?
Bar length.
Y is a variable, but what value of y? D, minus d to d, right? My integration is going to be from minus d to d on the y-axis, because that's where the charge lives. I don't have any charge except from minus d to d. Where I'm going with this is I want to integrate something, something, something dy from y equals minus d to y equals plus d. That'll capture all the charge that I have that is contributing to the electric field at my point of interest. That's where I'm going with this. So let's make a list of, if I'm going to integrate over y, I need to take careful stock of what depends on y and what doesn't depend on y. So depends on y and doesn't depend on y. I'll give you a freebie, of course. The constant k does not depend on which dq you're talking about, right?
R depends on y.
What does?
R depends on y.
R depends on, that's right. If you look at the different dq's, they have different distances to the point in question, right? So R does depend on y. So does theta, right? So if you're talking about a dq right here, the theta is what?
0.
0, but out here it's significantly larger, right? So theta also depends on y. We are luckily able to put lambda over into this camp because it's uniform, right?
But if it's not, you have to
If
do
it's not uniform, you would include it also in the integration. You couldn't factor it out, right? So just like over here, if this was a function of y, then you'd have to leave it along with all the other junk inside the integration. We are lucky enough that it is uniform and we just take it as a constant, okay? So another things to watch out for, future problems that I might give you that are variations on this one. What else do we have? We have lambda, k, r, theta. Yeah, that takes care of everything. I guess you could say I hat and j hat are constant, but that's kind of dumb. Okay? Those are constants, they don't change. So here's the problem. We can't integrate over y until we know how r and theta depend on y. We know that they depend on it, we just need to figure out exactly how. So our goal is going to be to try to get everybody on the same page. So let's go ahead and do that. This is where my Cartesian coordinates are going to come in really handy. I'll label x here. Of course, this right here is the x coordinate of my point in question. And then I guess I can label here, I should have probably already, but that's my y coordinate. So I can use Pythagorean theorem, of course, to get r here. And I can express r in terms of x and y, right? So instead of r, I'm going to replace it with x and y. So y is it right there in there explicitly. What about x? Does x depend on which point dq we're talking about? If we look at the different dq's,
No.
they all have the same x. They all have the same horizontal distance to the point in question, right? It's the y part that actually changes. That's the only reason r depends on y, is because of the dq's are in different spots vertically, not horizontally, right? So in fact, I'm going to replace this with y, and then x is going to live over here. So we're getting closer and closer to having a sort of sensible set of stuff to integrate over. This is the hardest part, by the way, of translating all the math you know to physics, because in physics it doesn't always come out that you know how to integrate right away. You have to get it into a form where everybody's playing nice. Let's work on the theta part. The theta part appears in a cosine and a sine, so let's work that out. This angle and this angle are the same because of some, I don't know, some geometry theorem that I don't care to remember the name of. Do you have crossed angles, opposite angles theorem or something? I don't know, whatever it's called. So we can say that cosine of theta, well, that's adjacent over hypotenuse. And sine of theta is opposite over hypotenuse. So just like that, we've got everything firing with the same variables. So we've actually gotten rid of theta as well in terms of x and y. Y is the variable we're going to integrate over, and x is just another constant. Okay? So at this point, we're ready to throw everything in and just do the job. This is where it looks like math class at this point. So let's go ahead and throw it in. It's going to be quite lengthy. So dE is equal to K times lambda dy over r squared. And then
sub in
cosine why am I drawing blank? There we go.
You're right.
And then minus, it was a minus.
Y over
and then-
square root.
Yep. And let me just remind you that this used to be the cosine of theta. This part used to be the sine of theta. And this, of course, used to be the dq. And this part down here used to be the r squared. Okay? Just in case I put in so many things that the whole thing is barely recognizable. Okay? All right. So now we're just going to integrate. Are there any questions before I do that? So I want to basically integrate all of my individual contributions. Put them all together. That's what you're doing when you're doing integration. So let's see what we get. Well, I'm going to pull out constants. So let's see, we have a k and a lambda, which is definitely constant. And then the first integration, I have a x and an I hat, which are constant. And then I have this ugly thing to the 3/2. Of course, this and this combined to the 3/2 power. Is that all right? Blah plus square root of blah is blah to the 3/2.
Mm-hmm.
Yes. Okay. And then what do I have over here? I have a minus sign. I have a j hat. I have a y dy. And then same ugly denominator. And I think that's good. So remember, you can pull out x as a constant, but you can't pull out y as a constant, because y is what we're integrating over. All right? So these look very familiar, probably to math class, right? This is the juncture where you can knock these out. You may, in math class, I feel like the constant is always a. Is that still a thing? I remember when I was a student, it's always integrating x squared plus a squared or whatever.
Yeah, exactly.
Okay, so just don't forget, we're integrating over y, and x is the constant. Okay, so again, x is constant. We're integrating over y. So looking at this, can anyone make their Calc 2 instructor proud and suggest a strategy for integrating this?
I think there's a property for x multiplied by.
What is it? Anyone want to take a stab? Is it a use sub? Trig sub, that's right. So this is the topic I keep on telling your calculus instructors, don't skip it, I need it. Okay? It's one particular instructor that will go nameless that seems to think that they're going to skip it every semester because it's quote unquote not that important, okay? It's important. How about this one? U sub. That's going to be a nice good old U sub because you got that y in the numerator, right? That's going to get you your U sub firing perfectly. So before we just say, I'm going to hammer home these integrations, I can do it. Let's work smarter, not harder. Okay. First of all,
Calculate.
I'm going to be able to say that the answer to this integration is 0. I'm not going to bother to integrate that because I can already tell. Here's how. I'll give you the math explanation and I'll give you the physics explanation. The physics one, for every charge up here that contributes a dy like that, a y component,
There's going to
dy,
be an opposite.
there's going to be one over here that contributes the opposite, right? That's one of the advantages of being on the perpendicular bisector, is that for every dq above, you have one below, and its y component's going to cancel out. If you're not on the perpendicular bisector, you have to do this, and guess what? On homework, you get to do it, okay? So this is 0 because you're on the perpendicular bisector. Now, if you want a mathematical explanation, here's your mathematical explanation. This is a sine. Yes, I made it look all crazy with Cartesian coordinates, but I'm integrating a sine. Is sine an even or an odd function?
Odd.
It's an odd function. Sine looks like this. Sine of theta versus theta looks like this. So if I integrate symmetrically around the origin, the area under the curve is always going to be 0. Okay? So that's what I'm doing, right? I'm integrating symmetrically from one side to the other. Some negative theta to positive theta, right? So if this integration bounds went from minus d to plus d, I can safely say that that goes to 0. If you're not on the perpendicular bisector, you have to do it. You'll do it on the homework. I basically set it up for you just now. It's a U sub. I'm sure you can do it. That's not to say that you have to remember how to do these things. You will find an integration table as well on your data, on your miscellaneous page. So if you don't remember how to do any of this integration, you can just use those. Now over here, I'm also going to point out this one came from a cosine. A cosine is what we call even or odd.
Even.
It's an even function. So if this is an odd function, I'm going to be lazy with the cosine too. Cosine looks like this, and if I integrate symmetrically around the origin, of course, I'll just get double what I would get on one side, right? So hopefully it doesn't bother you if instead of integrating from y equals minus d to d, it's always annoying to plug in a negative integration bound, so instead I'm going to put this to 0 and multiply by 2. See what I'm doing there? So any even function, so an integration of an even function from a minus whatever to a plus whatever is the same as multiplying by 2, integrating it half of it, right? Is this a thing that you talk about in math class?
Not really.
Hopefully. These are beautiful properties of even and odd functions that allow you to be super lazy about integration. Okay, so let's finish off this part next time.